Hey, this is Cooper. We had a lot of static coming from the mixer desk when we recorded this talk. As a result, I had to cut the first 2 minutes of audio, and for the first 40 minutes, the removal of a lot of the static resulted in the sound being rather distorted. We do apologize for this. It's a shame we didn't catch it sooner. I do believe that what remains is still audible enough to at least be workable. But yeah, we deeply apologize for this.
Project together. And the TechRain team has been creating this whole project and it grew really large, and to start from the actual exploit itself and make a fully fledged jailbreak out of it. So this is for the entire TechRain team. Not going to name all the people here. You can just check the slides later on. So this is like, who are us, not who am I. The TechRain team is a group of many people from the team around iOS hacking and jailbreaking both software and hardware. And it's actually, you might say, the best team of people that you could imagine to work with, given the single people's experience in different fields. So this is something that also, in my case, is really a pleasure to be part of this and work with these people, because it's like really an opportunity that you can just exchange all the ideas and work on something really huge that affects millions of people. So let's get right into it. Firstly, let's talk about SecureROM. SecureROM is the very first code that runs on the application processor when you start a modern device. It's basically a stripped down version of the iBoot. It's a part of the silicon, so it's not like a software component that you can replace, but it's like burnt into the actual silicon. And it's read-only, obviously, and you cannot just override it. And so getting access to it is already hard enough. So the only way to do it is by finding an exploit, which is also not easy, and try to circumvent its protection. This is also considered the most trusted code that runs on the application processor, because this is like the lowest point of the trust chain, because all other steps that follow it basically rely on the integrity of this component. And the main goal of the SecureROM is that it's supposed to load first stage bootloader that is validated. So it just does not run any bootloader, but like the very specific one, the one that the vendor wants, Apple in this case. And it also has features that allow recovery of the device in case like the file system got corrupted, or also possible to use that to perform a software update by uploading an image over USB. Usually software update is not performed in DFU mode, but you can start from the DFU mode. Like if everything is dead, then like all images are corrupted, then you have to start from DFU. Usually you enter the DFU mode by pressing a specific key combination of the device when it resets, and then you can start from the DFU mode. What comes next is basically the secure boot, and Apple or iOS is basically the ones who pioneered this concept of secure boot. It's, as I mentioned, a key part of the trusted boot sequence because it's the first thing that is just assumed to be trusted and not so it's the component that is supposed to be like integrity should not be corrupted. So when you want to start a boot image from DFU mode, the device is validating the integrity, and this applies to on-disk images, like on a device that already has the software on it, but also it applies to in-memory images, except for really old iPhones. So the ones that are non-volatile storage are also affected by these integrity checks. And that's why you could say that the secure boot mechanism is basically the number one enemy for jailbreaking. And because jailbreaking relies on bypassing these security checks, and either by compromising one of the nodes in the chain of trust, obviously the first element, which is the SecureROM, or by compromising a system that's already fully booted by other means. So I already mentioned DFU. DFU is a standardized kind of protocol that allows to transfer data with very simple USB control messages. And the basic goal is that you have like the least amount of code that needs to run to allow upload of like a boot image. And the data chunks that you transfer are uploaded with a special request to 0x21.1. And when the transfer is done, then usually there's a sequence of follow-up packets and a reset that will then tell the SecureROM to basically exit DFU mode and start to boot the image that you sent to it. But you can also exit this DFU mode with a specific DFU abort message, the 21.4, because you will see that sometimes you will actually have to control when you want to exit the DFU mode. So USB control transfers are the packets that are used to send data from the host to the device or request data from the device. If you make it a device lookup, then it's like device enumeration. It's sending a few packets back and forth. And the first packet is a header packet. It's a very simple structure and has a very it's just 8 bytes, and it just contains like basically the next packet is it should be like a data transfer or something. If the length field of the packet is non-zero, then it means that the packet will be, the next packet will be a data packet, like that's also called data phase. For example, in DP mode, that's how the data is transferred to from the hosted device. It could also be the other way around, but it basically depends on the request type. That's the first byte in the packet. The data phase basically allows to send data in chunks. Usually it has a specific size. It can be in different lengths, but usually it's a fixed length, and somewhere in the range between 8 and 64 bytes. And they are sent in sequence. And when the transfer is done, then it will send a zero length packet to tell the other side that this is the last chunk of data that should be transferred. In the iBoot stack, there's a temporary buffer that is allocated when the USB is initialized, and the data packet, the content of the data packet, they get then copied to this specific buffer as soon as they have been received. That's a very important detail. The USB stack is switched on as soon as you enter DP mode, and it triggers the allocation of this set buffer to hold the temporary data for the database. So once a transfer is issued, the pointer to this buffer will be copied to a global variable, which the stack will then use as destination for the data that comes in the following packet for the database. But exiting from DSU, it will actually turn off the USB stack. So it will also free the buffer that was allocated when it entered DSU mode. It stores a pointer to the buffer in a global variable, and it triggers the free of this set buffer when you exit the DSU mode. And it's never nulled out, so the variable will still contain the address of the previous allocation. And this is a request for use after free type of vulnerability. To trigger it, you basically have to start a control transfer, and with the data packet, like you have to specify the size, and then you have to interrupt the transfer, like during, like when it's still sending data, you just abort the transfer using a DSU abort. This will cause to free the temporary buffer, and then it will re-enter the DSU mode, because whatever you send is not a valid image. It will just fail, and then it will restart the DSU mode, and then it reallocates that buffer, and it tries to complete the previously interrupted transfer, actually, when it re-enters the DSU mode, and again, it will then copy the data that you send on top of the free pointer. So how does a practical trigger look like? Because this is all just theory, like, cancel the transfer and then hope that it somehow works out, but it's not that easy, because it's something that you just cannot really debug right away. It's not visible in front of your eyes. You don't see what happens if you try this. You need to create like an environment where you can really test this. And we had Little Lilo and Sugita using an Arduino board with a USB host add-on. This allows you to get full control on the USB host stack. And this is what you need if you want to be able to have faster transfers. Because most USB stacks they don't really let you do this unless you do some specific tricks. Luckily, the one on macOS basically has an API that allows you to abort the transfer, which is quite helpful. Yeah, and that's also what Atomic was using. Basically, abuse the stack in macOS to have it aborted at will. It's not deterministic, but like there's it's like time difference if you try this, but you can try it multiple times, which is helpful. And some of the USB, well, most of the USB sticks, in this case, IO USB, which is the macOS one, USBFS, that's Linux one, and there's WinUSB. They have a way to tell you how much data was transferred, because that's also important. So you get some feedback about the actual amount of data that was transferred, so you can basically profile the results and figure out like the best point in time for aborting the transfer. That basically gives you a practically deterministic implementation, because, as I said, it's actually not deterministic, so you need to figure out the best way to get it somehow reliable, or like the most reliable as it can get. I mean, without custom hardware, because if you have like full USB hardware control, then you can totally time this like very exact, and that could be possible, but it requires a lot of work, obviously. This is how the test setup looks like from SecureROM to pull this off. Yeah, but we actually are here for exploiting the SecureROM. So now that we know how we can trigger the vulnerability and make use of it, we want to see now how we can actually make use of it. So interestingly, on most devices, nothing would really happen because the way the code is designed. However, for the A8 and the A9, which are the older devices, they have a bug in the actual in the view handling code. The board functionality will basically leak a task structure whenever you do the view board, and yeah, that's what the user analyzed. And that was basically the first two SOPs that could have been exploited by this method. So how does it work? So you can corrupt the task structure, and when the system performs a task view, it will save the register into the structure, and when it's scheduled, when it's scheduled, the execution, it will restore the register from the structure, and use of the tree, it happens on the currently scheduled task. So you cannot overwrite the registers, because then it will, overwrite them again. However, the tasks, they have a linked list, and this list basically allows you to figure out which is the next task, that is to be chosen for scheduling, and that allows you basically to create a page path, the structure, so you can control what registers, like the register state. So when it executes it will restore the registers with the values that you need. And this is, you don't need drop or drop. You just need, it's direct code execution. You can just have it point to the cell that you want to execute, and it will run it. For 32-bit ROM, except the S1, which is the first generation Apple Watch. Also A7, A10, A10X, A11, A11X. They cannot use this strategy because these devices, they don't have this bug in the SecureROM user code, and there's no task vector that you can read to abuse it. And it also does not trigger any crash in the ROM. So it's deterministic enough so that the buffer is reallocated at the exact same place every time when the USB stack is initialized. So what we need is a way to somehow break this determinism so we can get an appropriate use FFP. Otherwise, we would just override the same region of memory every time the USB stack is initialized. Then it will effectively not allow you to have use FFP. So the allocator in the SecureROM, it basically gives you the smallest hole in the available memory for the allocation size that you have it, and this allows you to do a heap tree to basically lay out the heap for your purposes, and this is what SecureROM is used to create the use FFP condition, and for this to pull this off, we need controlled allocation for primitives. The USB transfers, they have a structure that is allocated on the heap, and you can also have multiple transfers happening at the same time. And like you can basically send multiple requests and then call the in endpoint. The device is waiting for more data, but you don't send it. And it will still keep them in memory for a while before disclosing them. And this is how you basically fill up the heap memory for a specific amount of time. And yeah, that's what we can make use of. And because of this delay, basically until it clears the condition of the stored packet and or the USB packet cut down, would allow you to if you have a specific layout for the heap. The problem is that for the allocation to test this, in case of UPC abort, it's part of the actual exploitation strategy. To shape the heap, what we want is to influence the next allocation for the buffer, because we want to put the threshold there. And there's a bug in the USB stack state machine that can be abused to basically have allocation that exists across the USB stack destruction and creation. So it executes remote, it destroys the USB stack, and then it enters the USB again, it's recreated, and there's still portions of memory that are still allocated. And the standard device request the structure sends the VLAN packet when the request is complete or when the stack cuts down. The problem is that when the stack is cutting down, the VLAN packet is never sent. It ends up being leaked. And this leak can be triggered conditionally as only packets that match specific conditions will trigger this leak. For instance, if it's not a multiple of 64 bytes, then it will not trigger the leak. Only if it's exactly 64 bytes. The reason is because that's kind of a weird thing with USB. If it's like if the last packet has the exact size of the packet length, then you have to send the zero length packet. Otherwise, it will not accept the zero length packet, and that's why it wouldn't trigger the leak. So you can use this leak on the heap to carefully craft the state of it, and then we have basically a hole in the memory area that has a specific size that will be used for a subsequent allocation. And also each of the USB request vectors that the USB code is like the USB handling code has the packet structure, and the structure contains function pointer to a callback. And so what we can do now is we can basically create a structure with the function pointer pointing to the tailcode that we want to execute and perform the use after free. So it will basically end up being an indirect branch whenever you call to your USB transfer or you execute use. And this is this strategy can successfully be used on the A9X, A10, A10X, and A11 SoC. Older devices have a problem because this leak is not always triggered for the in-flight USB request. But there's another strategy that you can use basically by filling up the heat. So it just takes longer to pull this off. If you just have to fill the heat until it reaches a point where just the remaining free memory has exactly the size that you want to have for the subsequent allocation for our target process. And checkmate. That's basically how we gain code execution. But this is just code execution. We want to do more of it, so we need to kind of create a bootkit to really have something useful. So explain to me like I'm 5. So we have code execution. The goal is to boot the device normally, but compromise the bootloader. So we basically end up being able to have the kernel pad, so we can have basically like disable the protection, and but this is it's quite tricky because if you want to support multiple devices and multiple versions, you don't want to manage like all the offsets for all these different devices and versions. So what you need is a patch finder that basically dynamically finds the locations to patch. And because otherwise it wouldn't be maintainable. Like if you just think of one iOS version, there are like so many devices already that you would have to cover that it's really a pain. And then you have multiple versions, which makes it even worse. And then you have new versions, which you still want to support without, starting from scratch and getting all the updates again. So, we need a patch finder. So iBoot makes use of a so-called boot trampoline, which basically gets the CPU state track to almost reset one, and it will wipe the previous boot image. If it's SecureROM, then obviously it's not wiping it, but it's disabling the access. It also disables NMU, and it wipes all the registers, including the X18 one, which is usually not used anywhere. So this is very easy to find if you just search for the move X18 0 instruction, because usually it's not present in any other code. And you can really easily write some shell code that is locating this. But there's a chicken and egg problem, because it will wipe the current state bootloader. So it has to be relocated from the bootloader into some memory that is not wiped by ID. There's a reserved region that is used for this, but on some versions, trampoline is relocated just before trying to use it, so it's really tricky. It's problematic because for the SecureROM, it's read-only, and we might get code execution before this happens, and in that case, it would mean it would wipe the bootloader, and we cannot make use of this text anymore. But we can relocate the SecureROM into SRAM with SecureROM and also a CCVR0EL instructions in order to remap the ROM range. On some devices, we can use a 512 kilobyte area for this. We can put the whole ROM in it. But on other devices, it doesn't have that much free SRAM that we can use for it. So in this case, you could use some exotic strategies to basically, like resize the heap to reserve more efficacious as addressable SRAM. But all we need really is to remap one single page in order to alter the sampling. So we don't need like the full image. And also we need to find the area where we actually want to set the cell code. But we're restricted to the available free SRAM. And also obviously we want to do a normal boot, which also uses SRAM. So maybe we can use DRAM. The problem is when SecureROM is running, it's still not initialized. So the first level bootloader is actually in charge of performing the DRAM initialization. The first level bootloader has a feature which is called soft view that basically simulates view modes, but it has DRAM available at this point in time, and it allows to upload a larger image to the view. This is what we can use to have an arbitrary amount of data, well, not arbitrary, it's limited, but it's big enough without having to initialize it ourselves. Large portions of DRAM can be saved by iBoot, but we can use a dirty workaround by basically hooking D0, and when we detect that the range that is supposed to be wiped out overlaps with the cell code, then we just make it enough that it's not doing anything. It's not really nice, but it works pretty well, so I think that's fair enough. So once the trampoline hook and the D0 hook are in place, we can reach the next trampoline invocation. Basically, we execute the hook in the next state bootloader if required. For devices before the A10, it uses 2 stages, A10 and later. They only really use one, so this is not really required anymore for new devices. So eventually the bootloader will have the kernel prepared, and the trampoline will be used in order to invoke the entry point to the kernel. On devices where ELC is present, we have the secure monitor, which is the entry point, and the kernel argument and the entry point are passed to it, so it can load it in year 1 for later execution. The hook that is performed on the trampoline basically means that we overwrite the branch target into the cell code that we uploaded, and then we pass it the original value in the register that we prevent from being cleared, and then get it to execute, and we can now patch the kernel. Like we have shell code, we can make it jump to it, and we run the shell code. The problem is, if you want to support many devices and versions without maintaining shell code for every single device, back to our patch finder, the problem is the way on you have the test trampoline to get the code execution, there's no MMU or testing enabled. And if you think about that, the kernel image is really large, and it will be just too slow for a viable attack. Because it needs so many memory accesses, and they basically parse like the whole kernel image, and that takes pretty too long. So what we do is we turn back on the MMU with a set of CPE instructions that will map a view of VRAM accessible. And then use that for the patch finder to work on that. Other than that, basically we just apply a pretty old school kernel patch test, because at this point in time there's no kernel patch protection, there's no kernel patch read only region. It's not initialized yet, so it's basically just back to iOS 8 again. So all these new mitigations were not present. And then we have the usual patches for VMware Protect, Reinforce Enter, the AMSI trust test resolution, sandbox, Mac framework hook, mount, test for POD0, the APFS file system, the remount. But it's not just the kernel that needs to be patched, because when the system boots, in user mode, if you want to prepare the device for jailbroken state, there's more to it. And so to do that, basically we embedded tiny vendors into the shellcode. Then we hijack the ER0, the user mode code execution, and then we patch the device key and the kernel boot argument structure. So we can map it, and then it will use that as the root device. So it basically starts off this. Wow, that has been some time that I heard that ringtone there. Anyway, you just cut off the noise. So instead of having it boot like the regular, use the regular root device, we basically have it use the small vendors that is prepared. And that's basically how this picture. Well, no, that was a little later, but it boots something else before the actual boot. So we started from the SecureROM code execution, got all the way to the EL user mode code execution, but the vendors need to be really small, because otherwise it would take just too long to transfer it to the view, because the view is meant to be just to transfer the next bootloader, and not like I don't know, like a 50 megabyte image or something. And it's just not a good experience if you have to wait for that long. So we needed a better solution for that. And it's not just that, it's also, there are also copyright concerns. If you just take proprietary code, put it in some vendors, and then ship that in like a publicly available tool, then Apple could technically go after us, which we obviously wanted to prevent you. But this is also problematic, because if you can't use the standard environment, then how would you start your own program on the vendor? So basically we need a dynamic linker and also some libraries that can link again, so we can have some useful code run. So what we did was we basically created a totally legitimate dynamic linker, and basically how it works is we use a syscall to mount the root file system on top of the small renders that we already mounted, but we're using the Unity mount, so we will not destroy the Bassen node of the process which is currently running. This will immediately shadow the DYV, the dynamic linker, more tricky than you might think because there's data protection, which basically means the user file system is encrypted, and until the system is properly initialized, you will not have access to it. So what you have to do is, we need to continue the normal root sequence. So it starts launch D.
So hopefully we will get access to the user data partition. So we need to do it somewhere early, but also not too late. We only need to make sure that data protection has been enabled, like access has been enabled. So what we do is we keep on using the union mounting trick to, in this case, use another disk image that is mounted on top of user libexec. Basically allowing us to replace any system daemon that is currently there with our own version. And we figured that the sysstatus check daemon that runs at some point when the device boots seems to be a very good timing across different versions, because that also differs how the system behaves, but this one was like the best choice. And then we execve our way back into a vnode from the original RAM disk, remember, the really tiny one, and then we forcefully unmount the user libexec image, because we want to have the original user libexec back. So that we have the system, like the integrity of the system is still kind of original. I mean, we already broke the integrity, but we don't want to break too much. So now we can have launch D continue booting just by basically calling execve on it. Then we can fork off before we do that, so we have our own code that is executed when the system boots. And we do that to basically allow to transfer another image. In this case, it's using USBMux, which is the communication protocol through the USB connection that is also used by iTunes and other tools like Xcode. And that uses like full speed USB. So we can basically upload whatever we want at this point. And usually what we need for an initial setup is, we want to have an SSH daemon so we can log into the device. And but we also want to have something for the user. So we install a checkbrain app, which in turn will allow the user to bootstrap the device by preparing the root file system, installing a package manager. And to do that, we basically mount on top of /binpack, which is the location that we chose for it. And then we kickstart the SSH daemon so we can log in. Sample image. And then once Springboard runs, the device continues booting, and at some point Springboard is running, then we will also have the checkbrain app. Okay, so this is the basic workflow of the jailbreak sequence. And when we created this jailbreak tool, we started with the macOS version, because first thing is we had the background research from Axiomix that demonstrated that you can easily use the IO USB stack on macOS to pull off this attack. But on other platforms, it was more complex, and that's why we couldn't just release like macOS, Linux, Windows version at the same time, because it's really a lot of work. So when ETA Linux version, it's already released. The thing is, why did it take so long? Many people didn't understand the reason for it. And if you rewind a little bit in this presentation, then
I already said that it's very critical that for the exploit to be usable, you need to be able to have partial control transfers that you can abort at a specific point in time. And the thing is that every platform is handling this differently, and it really requires some research and some tricks to get it to work on Linux, and in a somewhat reliable way. I mean, it's worse than on macOS, and it also depends on the hardware. For example, the Raspberry Pi 3 or the Raspberry Pi Zero, the USB controller is the way it's exposed to the running system will not allow it to perform the host-side USB attack. It's not that it's not possible at all, but it would basically require to directly talk to the actual USB stack, and it's just not it's just not something that you really want to waste time on. So basically, you have to go for a different hardware in this case. The Raspberry Pi 4, by the way, works so because it has a dedicated USB controller, but the previous generations have the OTG USB controller that is embedded into the SoC. So that's, by the way, it's basically the same one that's also inside of the iPhone, which is kind of funny, but it's the other end. So, yeah, and it's not just that. It's like this project has become so huge that you make so many weird mistakes. Like someone works on some code, and then someone else is continuing to work on it, and then you create some weird things like, oh, you can't really see that. Well, you will see. You can see it in the PDF that you can download later on. So basically, these are 3 commits that I just looked up because I remember this was like, why is this thing not working? That's crazy. It was working, and why is it not working anymore? And then it turns out there's an strcmp which is using the wrong size, and then I changed it, but it has a double negation in it, so it's like, you know, I fixed it incorrectly, and then I fixed it, but it turned out that this fix was, I mean, the compare was working, but the actual code wasn't actually expecting to get all these devices. This piece of code is basically telling us, oh, this is a USB device, so let's check if it's an Apple device and so on. But this was just giving us all the devices, and basically the last commit on the right, which you cannot really see, has like it just drop all of it and you know, have it search from the start. The previous compares were just looking for something that would never occur. So I was assuming something is wrong in the exploit, but it wasn't the case. It was just not finding the device at that point. And if you know, take like a few days to figure out why it's not working, it's like really disappointing sometimes. But you know, that's how it goes. It's not also, I mean, it's not just like simple human errors. It's more because Linux is very different, and it's a dependency hell if you want to support multiple platforms. And if you want to make a universal app, like, you know, you cannot just support all of them in an easy way. The reason is that usually there's also licensing issues that you have to take into account. So, yeah, I wrote like 3,149,377 easy steps. That's obviously just like a made-up number, but it took really a long time to figure something out, and we basically said, let's just focus on a small number of platforms that we want to support by using GTK3 with some in a package that the user can install, but still conforming to the licenses. But for the broader audience, like general Linux usage, the solution that we came up with was a static build that still complies with all the licenses. So TechRain 098 shipped with an ncurses UI, and also WebRain, which is like using ncurses
but makes it available through the web browser, which could be really interesting to use on like embedded devices. And this is something that Danny Lizansky and me spent lots of time on to get this UI working. The idea basically started at the CCC Congress last year. Or shortly before, but I spent quite some time to create the UI. But it turned out that was the best choice that we could make. When ETA Windows version. So this is still being worked on. The exploit itself works, but it needs still some work to package it up properly, to make a UI that is comparable to the quality standards that we made up for the other versions. Windows uses, for the Windows version, we're using USB-K stack for the DFU part. It also supports like the partial control transfers that we need. And the release is coming, but it's ready when it's ready. I cannot say it will be ready tomorrow. I was hoping we would finish it until today, but it still needs a bit of work, unfortunately. But well, we have the other versions, and who's using Windows anyways? So but what's new with checkra1n? Like what has happening in the past months? So I already mentioned that we published a Linux version with 098 with ncurses and WebRain. And it now uses Pongo OS. And also the kernel patch finder is a Pongo module. And since 0981, checkra1n also supports to load custom images that would be used instead of Pongo OS. Like you can create your own operating system if you want and start there. And also the internally used one, starting in this version, supports to load another custom bootloader. Well, and this is another slide. So what's Pongo OS? I just mentioned it. Pongo OS is the mini operating system, the name of the mini operating system that we came up with. It's a custom, really small, modular, low-level operating system that starts from DFU mode. Specifically for Apple hardware. It allows to bootstrap the device for other operating systems, and it's also open source since a few days. And we're still working on that to, get more device support, and there will still be a few updates coming for this. And also, we already have like a Linux that runs on top of Pongo OS. And in a further development cycle, there were a few people that came up with another idea to, create Android for the iPhone. And this is what we basically supported with the latest version. So you can now have Android on your iPhone. Because why not? So let's check out a few demos. We have like 3 minutes left or something, or 2 minutes. So I have like 3 demos, and they are like 2 minutes each, or 1 minute something each. So I think that will be okay. So the first demo I want to show is a battery-powered mini computer. It's the NanoPi M4, which comes with nice features like USB 3 USB controller, a dedicated one, not one of these integrated crappy OTG ones. And also, it actually has an NVMe adapter, so you can put like a SSD in it, which is quite nice. But that's not used for this scenario. So, let's see. Okay, yeah. So, no checkra1n app there. I'm logged into the Wi-Fi of this NanoPi, and I'm starting the command line version. the Encarsis UI version, which will now put the device into recovery mode first. It could also be totally automated, like you don't have to log in or anything, but it requires some timing to handle the actual DView reset sequence. So you want to be able to control that, until we figure out a better way to do it. But yeah, so now I'm entering DView mode, and then you will see it rain. Yeah, enter DView mode successfully. And now it's exploiting. There you go. All from the custom Linux version on the NanoPi. Okay. It will now boot into the normal operating system, and then, yeah, all done. And then you can see the checkRAIN app. I managed to find the home button. Yep. So that worked. Okay, next demo. That's actually the Windows demo. That was first showed at Blue Hat IL about a month ago, yeah. Or like 2 weeks or something. You can see it's still like using text mode for the actual procedure. Recovery mode. Now it will go into DView mode. By the way, there's also something really critical to this exploit, because people seem to assume that it doesn't matter how you enter DView mode, but it turned out that it's very critical how you enter the DView mode, because it can end up in a state that is not clean enough, and then the exploit might fail. So it still requires like the best way to enter it, which is what we implemented in the actual app to have the most clean state for the exploit. Okay. Yeah, the exploit already worked and the device is booting. Quickly write down the passcode. Yeah. And there's the checkRAIN app. Okay, and one more demo, and then we're done. We can have Android on the iPhone, and let's check it out. So I already did the first part, which downloads the image onto the device for later use. But it took like 14 minutes to download on the slow hotel Wi-Fi, so I don't want to keep you waiting with that. It basically creates a partition on the device, puts the NAND image, the Android NAND image on it, and then when you run the actual start sequence, it will use the checkRAIN app to enter Pongo OS, drop to the Pongo OS shell, and since we added the new capabilities to allow uploading boot images over USB in Pongo OS shell mode, we can have it upload from the command line here. We can have it upload the Android bootloader. This is what the script is basically doing. It starts the checkRAIN app, which expects it to be in DView mode. It loads Pongo OS in shell mode, and then it uploads the image. And now you will see something different happening. This is just Pongo OS for now. I first thought it failed, but there you go. 2 cores, Linux boot. That's quite fast. I mean, this is an iPhone 7, which is the first device that is supported. The others still require a bit of work. And by the way, we did not create the Android image. It's from the guys from Corellium that compiled and also open sourced the Android build. They call it Project Sandcastle, so it's projectsandcastle.org, where you can download the image. And yeah, as you can see, you have a running Android. The home button does not work, by the way, as you could see in the video. Yeah, that's it.
Thank you for sharing your knowledge. Any questions?
When ETA Windows? No?
No questions? Yeah.
Yes.
Hello.
Hi.
So, as per ARM trust zone architecture, it says that there should be dedicated RAM, memory, and bus for the trust processing. But here we are seeing that only ROM is separate and buses, registers, and all memory is being shared. Because of that only we have this path for exploitation, right?
I didn't understand the full question, actually.
Okay, so basically what I'm talking, ARM provide the trust zone architecture, which it says that the processing for secure part should be with the separate crypto accelerator, processor, memory, registers, and dedicated buses. And general purpose OS and hardware unit can only request for, okay, just verify me whether I'm right or not. Just tell me whether these things are trusted or not. This is the architecture what ARM trust zone says. But here we say that except SecureROM, everything is shared. Because of that only we could pass through with this exploit.
Yeah, because when you have code execution in SecureROM, you can bypass the security checks. You can supply another boot image and it will not check. I mean, the code that checks for the signature, it's just wiped out. So it's just knobbed and then you can just load whatever you want.
Okay. Thank you.
I hope that answered the question.
Yeah, somehow. What I understood yes, these things are being shared. That's the only reason it could give the path for exploiting the...
Yes, yeah.
Thank you.
Because you basically break the first link of the secure boot chain, and then, you can have all the following steps are the following bootloader images. You can basically break the integrity checks, and then you can load the next level bootloader, and then you can what we did. We created the Pongo OS, which is completely custom, totally from scratch. Code execution and creating an operating system environment. And since it's modular and it's also open source, you can start writing your own modules. We are about to release a new version which will have a module that basically disables the or re-enables access to the AES engine, so we can use that to decrypt firmware images, which was something really critical in the past, because as you see, you need an exploit to actually get access to it. Because the first thing that it does, it will disable access to the AES keys that are used for the firmware signing. So when the device is booted. And this patch will basically allow user mode access to these keys. So quite some interesting changes coming up, research-wise. Yes. Any more questions? No. Okay. Thanks for your time.